Hey, so welcome back. Now it's time to start implementing Newton's second law. What is Newton's second law? Well, Wikipedia is your friend, but here it is. The vector sum of the forces F on an object, which we've already calculated, is equal to the mass of the object multiplied by the acceleration of the object. So F equals ma. That's pretty cool. So we can rearrange that equation to work out what acceleration is. Well, it's F divided by m. You see, we're just dividing both sides of that equation by m, and then we're switching it round left to right. So the acceleration vector, which is a three-dimensional vector, is equal to the sum of all the forces, the big F, which we've already got, which is also a vector, which is why I've put it in bold, divided by m, which is mass, which is not a vector. That's why it's not in bold. Okay? It actually turns out that mass is something called a scalar. Like temperature, it can be on a scale, and that acceleration and forces are vectors. And you'll find out later in the course that both vectors and scalars are part of a wider family of things called tensors, which are real fun. We'll look at those a little bit later. Meanwhile, here's a relatively simple challenge for you. I want you to write the code for acceleration. We've really laid the framework, so it shouldn't be too hard. Publicly expose yourself a float called mass. Create an update velocity method. Inside that method, modify velocity vector every fixed update. And then remove debug.logerror code, because we now know how to deal with acceleration. Cool, so go ahead and see if you can make it respond to acceleration. The proof of the pudding will be when you have an unbalanced force, you no longer get errors, but you do start to see an increase in velocity that is proportional. So say that, for instance, you had just one force, that is, say, 2 in the x direction. That's 2 meters per second per second. Every second, you would expect the velocity in x to increase by 2. So you get 2, 4, 6, 8. That will prove you've got it right. Have a go. There's your challenge definition. Okay, cool, welcome back. So how are we going to do this? Well, let's make this new method called update. Oops, it filled in for me. Update velocity. Okay. Like that. It's a wishful method, it doesn't exist yet. And then let's write the method. Void doesn't need to return anything. Okay. So what did we say over in our slide? We said that acceleration is force over mass. All right, so we need to firstly work out what the thing's acceleration is going to be and then calculate how that changes the velocity. So for now, we only need access to the acceleration vector inside the update velocity. So let's keep it local to that for now. So vector 3. Acceleration vector. I'm being very explicit about the name of my variables here. A equals F over m. So what is the force? Well, it was the net force vector divided by mass. Autofill working against me there. I will make it conform. Okay, now mass is in red. Why? Because we haven't defined it yet. So at the top, I said let's make ourselves a public mass. Let's do that at the very top. Float is fine. We'll discuss floats and doubles and everything a little later. Public float mass. Acceleration vector equals net force divided by mass. Fine. So now we've worked out the acceleration. How do we change the velocity? Well, that's relatively simple as well. What's the velocity called? Velocity vector. So velocity vector. Oops. Plus equals acceleration vector, but times time dot delta time. Because the amount that the acceleration, the current acceleration changes the velocity depends on how long it acts for. Obviously, the longer you accelerate for, then the more increase in acceleration, in velocity rather. So the velocity vector equals the velocity vector plus acceleration vector times time dot delta time. I hope that makes sense for you. So we add the forces, we update the velocity, and then we don't need this unbalanced force detected anymore because it doesn't matter if the force is unbalanced. So we just then update the position. Now you could just put a comment in to say that's what you're doing. So I'm going to just have it say, so add forces, update velocity, update position, and it goes ahead and does it. Let's try it. Let's make sure we're starting with no forces. And we hit play. What happens? Nothing. Now we've got not a number, not a number, not a number in our velocity. Why? That's because our mass is 0. And it's the inspector overrides the code. So even if we initialize our mass over here to say 1 float and then try running, you may still find you have exactly the same problem because the inspector has overridden. So the key here is to set a mass. I'm going to set it to 1 for 1 kilo right now. Now hit play. It just sits there. Now let's give it a force. So let's give 1 force in the x direction. There's our little force arrow. But crucially, look, the guy is accelerating in x. Look at its x velocity, 7, 8, 9, 10, right? And its x position is increasing faster and faster and faster. Wonderful. Now if you were to add a second force to this guy, as say -1 in x, we have 2 equal and opposite forces. There is no acceleration, so look at the velocity vector, it's exactly as you left it. This is all Newton's first law, and the guy just hurtles through space as you'd expect it to. Isn't that pretty cool? You could now come in the y direction and say, well, let's add a third force, let's say. And let's give it, hang on, let me just sort this out. Let's give it 2 units of force in the y direction. There you go. Now what's it going to do? Well, in x, it's continuing at a constant velocity, but its position is moving because it's coasting in x. It's just carrying on as it was, but it's accelerating in y. So what force would you add to make this thing stop accelerating? Well, you would obviously need to do a -2 in y in this case, and now you have a balanced set of forces again. Again, look at the velocity vector in the inspector. It's still not moving. Awesome. It's moving, but the velocity is not changing. It's not accelerating, but the position will continue moving. Now, there's no quick, simple way to bring this back to a halt in the global reference frame. You actually have to just decelerate it down to a standstill, and it's going to be nearly impossible to do that. If I put y equals -4 on this second force, for example, then watch what happens. The y velocity will drop, 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 and of course the y position is still going up at the moment because it still has a positive y velocity. Eventually the y velocity will go negative, and then the position will start to fall down again. So I mean, you may have this inclination, oh, I want to put this thing back at the origin. Well, kind of bad luck. There is no origin in reality. It's this starting to show how arbitrary our point of view is. Once it's stationary in our point of view, like it is here when I have equal and opposite forces, it's stationary in our point of view, but it still has a velocity. And it's still moving. So if it upsets you that it's moving through space, let go of that. Consider the idea that it's not having any relative change in velocity. That's kind of what matters. You are hurtling round the Earth at 900-ish miles an hour now, and the Earth's hurtling around the Sun, and the Sun's hurtling around the galaxy. Movement is a relative, is always a relative. So this guy is moving, but he does have balanced forces on him. So hopefully that all makes sense. You've now gone yet another step, and you can actually model arbitrary forces all adding together on this thing, leading to the correct accelerations. So that's wicked. You are now modeling Newton's second law. Great job.